When you're faced with a huge, complicated, wicked problem, where do you even start? It can feel impossible. This standard, HS-ETS1-2, is the answer to that question. It's the professional engineering way to take on a challenge that seems too big to handle. The big secret is, you don't. You don't solve the whole problem at once. You divide and conquer. You break it down into a list of smaller problems that you can solve. So what's a complex real-world problem? It's not a simple math question where 2 + 2 = 4. It's a messy problem from real life. Designing a self-driving car is a great example. There are thousands of interacting parts, sensors, software, brakes, ethics, and a perfect solution doesn't exist. A mission to Mars is another. You have to solve for food, fuel, radiation, and landing all at once. These are systems problems. Our job today is to learn how to think in systems. This is the official standard we're tackling. It's all about process. It says we need to design a solution. But how? By breaking it down into smaller, more manageable pieces. This is the exact same process used to build your smartphone, design a video game, or plan a city. You're learning the fundamental framework of engineering. How to take a big, messy idea and turn it into a step-by-step plan. The one-word summary for this entire standard is decomposition. It's a powerful idea. You've probably heard the old riddle, how do you eat an elephant? You can't do it in one gulp. You do it one bite at a time. Decomposition is the engineering version of that. It's how we take that impossible, elephant-sized problem and break it down into a series of bite-sized problems that we actually know how to solve. Let's use a perfect analogy. Building a car. If I told you, go build a car, you'd be stuck. But what if I told you, go build a system that makes wheels stop spinning? That's a brake. You could figure that out. What about build a system that turns burning gas into rotation? That's an engine. A car isn't one invention. It's a system of systems. It's a solution that's also been decomposed. The engine, brakes, and steering are all subsystems, solved by different teams that all work together to solve the bigger problem. I need to get to work. Why do we do this? Why bother breaking it down? First, it gives us clarity. It's just way less overwhelming to focus on designing a brake pedal meant to think about the whole car. Second, it allows for specialization. This is key. The person who's a genius at a car's electrical system probably isn't the same person who's a genius at its engine. This lets teams of experts work together. And finally, it lets you test parts individually and build them at the same time, which is just way more efficient. Okay, let's run a real case study through this process. Our complex, real-world problem is this. We need to provide clean, safe drinking water to a remote village. This is a classic global challenge. It's big, it's messy, and it affects human lives. If we just show up with a bunch of random pipes, we'll fail. We have to be smart and decompose the problem first. So let's act like detectives. Why is this a problem? Let's break it down. First, the source. The only water they have is a river, and we test it. It's full of bacteria. That's subproblem number 1. Second, distance. The river is a long walk from the village. People have to haul heavy buckets. That's subproblem number 2. Third, infrastructure. The village has no electrical grid. We can't just plug in a filter. That's subproblem number 3. And fourth, usability. Whatever we build, they have to be able to fix it themselves. We can't fly in an engineer every time a part breaks. This is the aha moment. If the problem has at least 4 major parts, our solution must also have 4 major parts. We can't just solve one. If we only filter the water but don't get it to the village, we failed. If we only get it to the village but don't filter it, we failed. So our solution won't be one thing. It will be a clean water system. And that system will be made of, you guessed it, Subsystems. Based on the problems we identified, our clean water system needs to have 4 main modules. First, a collection system to get the water from the river. Second, a purification system to kill those germs. Third, a power system to make the other parts work. And fourth, a distribution system to get the clean water to the people easily. Now, instead of one giant problem, we have 4 smaller, manageable problems to solve. Now we get to the multiple solutions part of the standard. This is the brainstorming phase, and it's where real creativity happens. For each of those 4 subsystems, we are going to brainstorm at least 2 or 3 different ways to solve it. We're building a menu of options. We want to have choices, so we can pick the best combination later. Let's start with purification. How can we kill the bacteria? Option 1 is a UV filter, a special light bulb that zaps germs. It's high-tech and effective. Option 2 is a ceramic filter, which is more low-tech. It's a clay pot with microscopic holes that are too small for bacteria to pass through. Option 3 is chemical, like a simple, automatic chlorine drip. All 3 work. They are all valid solutions to this one subproblem. Next, let's brainstorm for the power subsystem. Remember, there's no grid. So, option 1 could be solar panels. This is high-tech, but free energy from the sun. Option 2 could be human power. Think of an old-fashioned hand pump or a pedal-powered machine. Option 3 might be a diesel generator. It's reliable, but it requires a constant supply of fuel, which might be a new problem. See, there are trade-offs for everything. Finally, let's brainstorm for distribution. How do we get the finished clean water to the people? Option 1 is simple, a single tap right on the machine. People come to one spot. Option 2 is more complex, a water tower. We pump the water up to a big tank, and gravity delivers it through pipes to taps all over the village. Option 3 is just a batch system, where the machine fills a big tank and people come and fill their own jugs. This is where it all comes together. We've created a solution matrix. It's a menu of choices for each of our 4 subproblems. Now, we can act like chefs. We can mix and match one option from each category to create a complete solution. This is how we design a solution. In fact, we're not just designing one solution. By doing this, we can easily design 3 or 4 different complete systems. Let's build our first complete system. Let's call it the high-tech model. From our menu, we'll choose the electric pump, the UV light filter, the solar panels, and the water tower with multiple taps. This is a complete, valid solution. It solves all 4 of our subproblems. It's convenient, automated, and provides water all over the village. It's a great design. But is it the best one? Now let's build a second one. Let's call this the low-tech model. From our menu, we'll choose the manual hand pump for collection. This pump also provides the human power, so it solves 2 problems at once. For purification, we'll use the ceramic filter. And for distribution, we'll use the single tap. This is also a complete, valid solution. It also solves all 4 subproblems. It's a great design, too. So, now we have 2 excellent but totally different solutions. How do we choose? This is where we link back to our last standard, HS-ETS1-2. We have to go back to our criteria and constraints. Remember those? Criteria are our goals, e.g., must provide 100 liters a day. Constraints are our limits, e.g., must cost less than $5,000 or must be repairable with local parts. Let's evaluate our 2 designs. The high-tech solution is amazing. It meets the convenience criterion perfectly, but it's super expensive and complex. If a solar panel's inverter breaks, the whole system is dead. It probably fails our cost and repairability constraints. The low-tech solution is the opposite. It's cheap and can be fixed with basic tools, so it passes our constraints. But it's slow and requires a lot of hard work, so it might not meet our volume criterion. The key is, there's no single right answer. There are just trade-offs. To wrap up HS-ETS1-2, just remember this. No one solves a wicked problem by just jumping in. You stop, you think, and you decompose. You break the big problem into small sub-problems. Then, you design a system of sub-solutions to match. You brainstorm multiple options for each part. This lets you assemble several complete, competing solutions, which you can then evaluate to find the one with the best possible trade-offs. That is high-level engineering.